So let's suppose the omega is 0, then this is the original projectile motion that you get. Okay, if I give it some kind of a spin, let's suppose 5 units, then the path traces inwards towards the goal compared to its original projectile path. But if I give it slightly greater, let's make it 10, now then it approaches the goal post, but again I'm not really that good at it. But if I make it, let's suppose 15, then I've hit the goal there. I've hit the goal there, you see. Okay, so there you see it. The footballer kicks the ball and it is supposed to go along this particular direction, but because of the spin and because of the Magnus force, the path curves and it comes and sort of hits the goal there. You see that?
Smashing through it, but it's going to be hard otherwise. It's Ronaldo. Oh, he's done it! He has only gone and done it! Cristiano Ronaldo! Sensational free kick! A brilliant hat-trick! A magnificent game! Portugal 3, Spain 3, Cristiano Ronaldo.
Let's take a look at that one more time. Let's take a look at the goal, okay? Yeah, the ball is going in this particular direction, right? You can see the ball going in this particular direction. But at some point, it slightly changes its trajectory from where it was supposed to go, right? We all have experiences with projectile motion, how when you throw an object, it goes along a particular path. But the ball seems to go outside the goal posts, but later on, it curves its path and goes inside the goal post. Exactly, there it is. So it went outside and then traced its path inside the goal post. Okay, so let us study what we just witnessed. We witnessed what is known as Magnus Effect. Okay, so first of all, welcome back to my channel. I am Divya Das and this is For the Love of Physics. What happens is that whenever you have an object that is traveling through a medium like air and it is spinning, then the spinning object experiences a force in a particular direction which is not the same as the direction of its velocity. And because of the force that it experiences in some other direction apart from its velocity, the path of the particle changes, and this phenomena is known as Magnus Effect. So let me draw a diagram to explain what the phenomena is first. So let's suppose that this yellow colored circle, which is like a football, is traveling through a medium like an air and it is going in this particular direction. Okay. Now the football is going towards the right. It simply means that if the surrounding air or the fluid was originally at rest, then relative to the football, the fluid will be traveling towards the left. Yes. So the direction of the fluid with respect to this football will be in this particular manner. Okay. Now let's suppose that the velocity, the relative velocity between the football and the fluid is given by v. Now what is going to happen because of the interaction? Well, if there is no spin to the football, then the nature of the interaction on the top and the bottom half is going to be similar. So there is not going to be any kind of a additional force perpendicular to the direction of its motion. Of course, there is going to be a drag. I am going to account for drag later on. But what if the football was spinning? So let's suppose the football was spinning apart from going in a linear direction. Let's suppose in this particular manner with angular velocity of omega. Now, if this was the case, what is going to happen is that at two different locations, let's suppose this is point A and this is point B, the relative velocity of the fluids is going to be different. The velocity of the fluid at point A is simply going to be equal to the original relative velocity, right? What is the relative velocity of the fluid? It's v, right? If the football is traveling forwards at v, then relative to the football, the fluid is traveling towards the left with a speed of v. But at this particular point, because the football is turning in this direction and the fluid is also going in this particular direction, then there is going to be an additional term here plus omega cross r. Okay, if a circular object is rotating, then what is the linear speed corresponding to a particular point on its circumference is given by omega cross r. Similarly, at point B, the speed of the fluid is going to be slightly decreased because it's the football's circumference is going in this direction, the fluids are going in this direction. So it's going to cancel out some of these quantities and I'm going to get V minus omega cross r. What this does is that it creates a difference in the relative velocity between the fluid sections at the top and at the bottom of the football, you see. And what happens whenever the fluid flowing across an object has different velocities at different points? Well, this conclusion comes from a very common principle in fluid mechanics, which is known as Bernoulli's principle, that says that if there's a velocity difference between two different points of an object, then it leads to a pressure difference also. The pressure difference creates a force that the object experiences in a particular direction. The velocity is greater here, it is lesser here. That means the pressure is higher at point B compared to point A. That means there is going to be a gradient of pressure in this particular direction, which is going to result in the force which we are going to call as Magnus force. So you have this Magnus force, I'm going to call this as Fm, acting in a direction perpendicular to the direction of its motion. This will create a situation in which, in the absence of the spinning, the particle was going to go in this trajectory, but in the presence of this Magnus force, the particle's path gets deflected. You see what's happening? This is what we are going to study today. So if the object was traveling towards the right, but it experiences this kind of a additional force, then its actual trajectory, instead of being in this direction, ends up becoming something like this. This is the actual curved path of this particular ball. Now I want to simulate the same situation as if a footballer kicks a ball. So if a footballer kicks a ball high up in the air, then that is supposedly a projectile motion, because you throw an object high up in the air at a particular angle with some kind of a speed, it goes up and comes down because of gravity, it creates a projectile motion. So I want to simulate a projectile motion, but I'm going to add a drag as well as the Magnus effect in that kind of a projectile motion and see what results we get. Now the question is, how do you calculate this kind of a force corresponding to Magnus effect? Well, the force corresponding to Magnus effect is essentially proportional to omega cross product with V. If V is, let's suppose, the original, what you can say, velocity of the object because of its linear motion, and omega is the spin of that particular object, then omega cross V is going to give us the direction in which the Magnus force is being applied on. Now, of course, this is not the entire term. There are other terms involved. I'm going to represent the other terms with K here. What is K? Well, K contains many other things. You see the total Magnus force that is acting on the football depends first of all on the shape of the football, right? If it is a football which is a sphere or a cylinder or some other kind of an object, it depends on the nature of the fluid, it depends on the density of the fluid, it depends on the volume of the object, the shape, the size, various things. So the dimensions, the volume, the shape, the size of the object, the nature of the medium, all of this contributes to a particular magnitude, but the direction is basically given by omega cross V. So I'm going to keep K here just as that particular constant that is attributed by everything else that I talked about. Now, depending upon what kind of a system you are studying, you can substitute all those parameters in this particular K here. So let me trace out a simple trajectory that I am expecting. Let's suppose this is the X, Y, Z three-dimensional space, and we have some kind of an object that creates a projectile motion. Okay, something like this. So basically, initially the object was kicked at a particular initial speed. So the footballer kicks the ball in a particular direction at a particular angle, let's suppose, and the ball is given some kind of a spin. So let's suppose I'm going to create a situation where the ball experiences a spin of omega along the y-axis. Let me call this as Z, and let me call this as y. Doesn't really matter as long as I write the equations properly. So let's say that the spin is the omega is such that the omega vector has a direction along the z axis. I am not going to change this during the course of its motion. Okay, so if the ball reaches somewhere here, it still has a spin in this particular direction, and if the ball reaches here, it still has a spin in this particular direction. Now, of course, in a real life situation, there are different kinds of factors, but to make the calculations easier, I'm going to keep some of these things ideal. So the spin is going to be constant of motion, let's suppose. So as the football is kicked, it tries to trace out a projectile motion, but it is also spinning in such a manner that the football has a omega direction along the z axis. Okay. Now, of course, there are other forces involved. So let's suppose if I draw the football mid trajectory, it has a force, the gravitational force mg along the downward direction. Okay. It also has a force which is a drag force. You could trace out the drag force also. So let's suppose a drag force is opposite to its motion. So if the ball is going to trying to go in the right hand side direction, the drag will be opposite to its velocity. I'm going to call this as Fd. Now usually, again, it depends upon the nature of the fluid, but usually the drag force is proportional to the instantaneous velocity of the object. So I'm going to call this as Bv. Okay, v being the instantaneous velocity, b being some kind of a drag coefficient. Now, what would be the direction of the Magnus force? As you can see, the direction of the Magnus force is given by omega cross v. So if you visualize it using your right hand rule, then essentially the Magnus force is directed towards a negative y-axis. Anyways, it's going to show up in our calculations anyways. Let me just write down the equations involved. So k I'm going to keep outside, and let us look at what are the different kinds of parameters we have. So because this is a cross product, so let me write down the different parameters. What is v? V is the velocity, the instantaneous velocity. So I'm going to call this as x dot, y dot, and z dot. So these are the time derivative of x, y, and z. But what about omega? I am saying that omega has a direction along the z axis. It's a constant of motion. So I'm just going to keep omega here, and rest along x and y, the components are 0. So this comes out to be k I cap minus y dot omega plus j cap x dot omega plus k cap 0. Okay. So this comes out to be k here, again depends upon the detailed nature of the problem. I'm just going to keep it as a k. I'm just going to give it some unit, okay, because I'm interested in doing a qualitative simulation as of now. And here I have minus y dot omega I cap plus x dot omega j cap. Now let's write down the detailed equation of motion from the Newton's second law, which tells us that the net force acting on this object is equal to mass times acceleration. Okay, so what is the net force? Well, the net force is essentially the Magnus force as well as a drag force and the gravitational force, of course. So the gravitational force plus the Magnus force plus the drag force. Okay. Now, what is the gravitational force? The gravitational force is acting in the negative z direction. So I'm going to say that this is equal to minus mg k cap. Magnus force I'm going to substitute from here. Okay, I'm going to substitute from here, which is minus y dot omega I cap plus x dot omega j cap, and the drag force, which is nothing but b x dot I cap plus b y dot j cap plus b z dot k cap. So this is equal to mass times acceleration, right? So if I combine these terms and separate along the x, y, and z components, this should give me something like minus mg plus b dz upon dt. So if I separate out these individual sort of coefficients along x, y, and z axis, I'll get 3 second order differential equations corresponding to the x, y, and z directions equations of motion, right? So the first one I'll get is, this is along the x axis. By the way, there was a k here, right? I kind of forgot about the k. The k was here. So a k here minus k, and the k here plus k minus k and plus k omega. Okay, this should reflect somewhere here. minus k by m and b upon m. Similarly, I should also get along the y-axis. So if you compare this term with this particular term, I should get this equation. And similarly for the z-axis, if I compare this with this term, I will get an equation. Yeah. So I have 3 second order differential equations that need to be solved if I want to simulate the banana kick or the Magnus effect of a football being kicked in a particular direction. So how do I solve these 3 second order differential equations together? Well, to do that, we can use some kind of a computational software. I'm going to use Scilab. Scilab provides inbuilt commands to solve differential equations. Therefore, I'm going to use Scilab. I have previously made a couple of videos explaining how Scilab works, the various syntaxes and commands. If you're new to Scilab, you can go through those videos to get an idea about this kind of a computational software. If you're familiar with any other kind of a computational software, maybe MATLAB, maybe some programming languages like Python or C++, then you'll have to create a program on your own to solve a differential equation. Okay, you can do that according to whatever commands and syntaxes are present in those platforms. What I am going to do here is I'm going to simplify these 3 second order differential equations into 6 first order differential equations, because Scilab provides a ODE command to solve a first order differential equation. So I'm going to create 6 first order differential equations and I'm going to create a program to sort of solve this problem and then look at the interesting results. To do that, I'm going to make a couple of substitutions. Let's suppose that x is equal to x1. Okay, if I make this substitution, that x is equal to x1 and dx upon dt or dx1 upon dt is equal to x2. Okay? In that situation, what is d2x upon dt2? That is nothing but dx2 upon dt, right? Because x2 is equal to dx upon dt. So therefore, dx2 upon dt is d2x upon dt2. This is equal to minus k upon m omega. Rest I'm going to keep empty here. I'm going to fill it in a little bit of a moment after completing the other substitutions. Let's say y is equal to x3. In that situation, dy by dt is equal to dx3 upon dt, which I am going to assume to be x4, and d2y upon dt2 will be therefore dx4 upon dt, which is equal to k upon m omega. Rest I'm going to keep empty. I'm going to fill it a little bit later on. And here z is equal to, I'm going to assume x5. So dz upon dt, I'm going to make another assumption that it is x6. So d2z upon dt2 is dx6 upon dt, which is equal to minus g plus b upon m. Okay, so let's fill out the rest of the details. For this, what is dy upon dt? So dy upon dt is x4. So here I'm going to write minus k by n omega x4 plus b upon m. What is dx upon dt? That is x2. So x2. All right, done. What about this particular case? So k by m omega. What is dx upon dt? That is x2 plus b by m. What is dy upon dt? That is x4. This equation is done. What about the last equation? This one. So this is b by m dz upon dt. That is x6. All right. So I've made a couple of substitutions. x1 is x, x3 is y, and x5 is z. Okay. And dx upon dt is x2 and dy upon dt is x4 and dz upon dt is x6. The reason I've done this is because it simplifies the problem of simultaneously solving 6 differential equations using ODE command in Scilab. Now let's go to the Scilab platform and try to create this necessary program. So here I am in the Scilab platform. Let me first enter some of the constants I'm going to use. So k upon m, okay. Let's keep some small value like 0.01. Again, this depends upon the detailed nature of how the interaction of the object with the fluid takes place. But because I'm doing a qualitative study of the trajectory, I'm just keeping it some value. Let's suppose b upon m. So k upon m, I'm going to call that as km, and b upon m, I'm going to call that as bm. I'm going to keep that, the drag also some small value. Again, something like 0.01, okay. Omega or w, I'm going to give it some value. First, let's take the 0 case and then I'll look at other cases. To solve a second order differential equation or 6 first order differential equations, what we need to do is we need to replicate a function where I represent the right hand side of all these equations as rows belonging to multidimensional matrix. Okay, so to do that, let me define a function. So what I need to do here is I need to represent within this function the right hand side of these first order differential equations. Okay, so let's suppose the first order differential equation is dx1 upon dt is equal to x2, right? So here I'm going to write x2. The solution of the ODE is x, but x2 is actually the second row of that particular multidimensional matrix X. Okay, and then for the next I have minus k upon m omega x4 plus b upon m x2. Alright, so I've written for the first two equations. Let me write down for the other four equations also. Alright, so all these six differential equations, their right hand sides are essentially, for the first two you have this, for the second two you have this, for the third two you have this. Okay, you see this? For the first two differential equation, for the second and third, for the third and fourth. Now, I need to give it some initial values. So let's suppose time starts from t0 is equal to 0, and I need to give the position and initial speed of the ball, right? So basically, what we had was we had x1 and x2 and x3 and x4 and x5 and x6. If you remember, x1, x3, x5 represents the position coordinates xyz, and x2, x4 and x6 represents the time derivatives of xyz, which is the velocity component. So let's suppose we start with a position of 0, 0, 0, which is at the origin, but I give it some velocity component. Let me give some random numbers. Okay, let's take 30 along the x-axis. So vx is 30, vy is 30, vz is 30. So it's at a particular angle. So the projectile is thrown at a particular angle upwards with speed such that the components are 30, 30, 30 meters per second. The solution of this differential equation, the six differential equations, is essentially x is equal to ODE, the initial conditions, x0, t0, and then across a range of time. So I need to give some time. Let's suppose t is equal to from 0 with a step size of 0.05 up to 6, and the function is fx. So this will give us a solution which is x. Now I want to plot this in a three-dimensional sort of a plot. So for that I'm going to do this. This should create some projectile motion. Let's see. Yeah. Okay. So here I have a projectile motion. Okay. So it starts from the origin. So let's suppose at the origin the footballer kicked the ball. It creates this kind of a projectile. You see, the ball has been kicked upwards. It goes up, comes back down, and it falls on a particular surface. So let me try to simulate a situation in which the footballer, let's suppose, kicks a ball in a particular direction, but he tries to hit the goal, he tries to put the ball within the goal posts. So can we tweak the values of omega and sort of look at the trajectories, and can we hit the sort of a goal using some random values? So let's try to do that. But let me create the goal posts first. Okay. Essentially, these lines of code simply just create the goal posts. Okay, don't worry about it. It's just to create a goal post. So yeah, so you see that. Let's suppose that this is the goal post that we have. Yeah, this is the goal post. So let's suppose the goalkeeper is somewhere here. All right, you see that. Let's suppose this is the goal, and the footballer is somewhere here. He sort of kicks the ball goes up as a projectile and falls somewhere here. Now what's going to happen if I tweak the various parameters? I already discussed the effect of the Magnus force is that it is working in the direction perpendicular to the velocity, right? So therefore it curves the path. So initially I have kept spinning 0. So in the absence of spin, there is a somewhat drag to the projectile, but in the absence of spin, this is the nature of the projectile that I essentially get. What if I give it some spin? Okay, let's give it some spin. So what if I give it a spin of, let's suppose omega is equal to 5. Okay. If I give it a spin of omega is equal to 5, again, these are some numbers that I'm randomly taking to give me sort of a qualitative idea of what's happening. And then I plot it. There you have it. You see, the trajectory is different compared to the original projectile motion. So the original projectile motion is this one, right? This is the original projectile motion. If you look at it like this from upwards, it's kind of a straight line if you look at it from a top view. But the blue or the purple line, the path curves towards the left. If you look at the three-dimensional view, the path curves towards the left in this particular manner. You see this? So the banana kick or the or the curved kick sort of, because of the spin, the path changes slightly. Now, can we hit the goal post? Let me try out a value. Let's suppose omega is equal to 10. Okay, let's keep omega is equal to 10, and if I run the program, yeah, I think I've hit the goal post. No, it went a little bit above the goal, right? It sort of hit the post and probably went outside. What if I change the values a little bit? Let's suppose I take this 15 and no, I think I need to reduce the initial velocity along the y direction by slight amount. So let's suppose initial velocity along the y direction, decrease it slightly. Okay, let's make it 28. Let's see what happens now. Now I think I'm going to hit the goal. Let's make it 25. Yeah, exactly. There you have it. You see, by tweaking the spin, now I've hit the goal post. Okay, let's redo this again. So let's suppose the omega is 0, then this is the original projectile motion that you get. Okay, if I give it some kind of a spin, let's suppose 5 units, then the path traces inwards towards the goal compared to its original projectile path. But if I give it slightly greater, let's make it 10. Now then it approaches the goal post, but again I'm not really that good at it. But if I make it, let's suppose 15, then I've hit the goal there. I've hit the goal there, you see. Okay, so there you see it. The footballer kicks the ball and it is supposed to go along this particular direction, but because of the spin and because of the Magnus force, the path curves and it comes and sort of hits the goal there. You see that? If I increase the spin, the curve would be much more higher and it probably escape, I think, this thing, the goal again. Yeah, you see that? You see that? So you see how interesting this is. We have simulated the projectile motion of the football kicked by a footballer, and we have accounted for drag, we have accounted for gravity, but most importantly, we have accounted for the Magnus effect, so that the nature of the path traced out by the football looks something like this for varying degrees of omega. You see? So the original projectile motion is this one, but with increasing omega, the particle's trajectory sort of traces out in this particular manner. So you see, professional footballers, they probably have a very good intuitive idea of what amount of speed the ball should be kicked at, what amount of spin should be given to the ball, and from what distance, and based on their experience, they are able to hit the goal perfectly. But we, as a physicist, we have just simulated the similar problem with just changing and tweaking the parameters involved in our differential equations, and we have been successfully able to do the same thing. All right, so this is so interesting, right? Extremely interesting sort of a simulation. Wow, awesome. All right, so I hope that you enjoyed this particular simulation and the formulation of the problem. I'm Divya Jyoti Das. This is For the Love of Physics. I will see you next time, guys. Thank you very much. Have a nice day.